Thank you. You hear me, I'm sure. So today I'd like to present our recent research about shock-induced melting and crystallization titanium. This kind of combined work consists of experimental and simulation part. Most of listed here, my co-workers are experimentalists. Okay, next. So recently, just past decade, the shock laser pinning technology, kind of new technology, using nanosecond laser pulse was developed. It is very useful for improvement mechanical properties of working phase on tools or materials. However, this technology is used many great number of nanosecond pulse, and each pulse is has quite low energy and generate a low pressure shock wave with pressure about 1 GPa. By contrast, ultrashort laser pulse with duration less than 1 picosecond may produce much higher density of deposited energy. So short but very strong shock wave, larger than 100 GPa, means 1 megabar, can destabilize the lattice, the crystal lattice, and causes melting and recrystallization of solid. Our main question was what the thickness and atomic structure of subsurface layer modified by such strong shock wave. Of course, we're also interested in the fundamental mechanism of such modification. So we performed experiments and the molecular dynamic simulation to research shock-induced evolution of material. So recently our work was published in Physics of Fluid in September issues this year. And graphical abstract on the top illustrate three main parts of our work. So experiment was performed with a laser pulse having energy about 5 joule per centimeter square, but emitted for very short duration, 100 femtosecond. This pulse hit the surface of the target, just pure titanium. Of course, in the middle, you see simulation results, because we have no access at such early time, within just several nanoseconds, for evolution of the material. Just with the same day, or maybe after one day, the sample irradiated by this laser pulse was analyzed using electron microscopy, transmitted electron microscopy of the subsurface layer. And you see on the right side here that indeed surface of material modified significantly. So what we found in our experiment, the formation of two modified subsurface layers. You see on the left image scanning transmitted electron microscopy of single crystal piece lamella extracted using focused ion beam from the bottom of the crater. At the top, of course, there is some protective layer which protect underlying material from the ion beam. Should not be destroyed in the electron microscopy. And layer B, mostly deeply modified, and we think it happens due to propagation of melting shock wave and recrystallization of material in this B layer. Its thickness is about 1 micron. Below this layer, we see layer C, also modified layer. However, because attenuation of the shock, the amplitude of shock was not enough at this depth, and the melting does not happen. Instead, the elastic plastic transformation still continues, and the recrystallization resulting in formation of new microcrystalline structure may happen here. Below, in zone D, the material stay just intact as with this initial crystalline structure. So in order to make more detail, to see more detail, the high contrast dark field image was taken from this green square, and you see elongated vertically crystalline grains, which directions almost coincide with direction of maximum heat flux, because on the top we have a high temperature and in the depth low temperatures. The heat flux is oriented vertically. So a red square demonstrates some very strange, unusual behavior with a different orientation of the newly formed crystalline plate. Actually, we have not analyzed what happened here because it's just exception. Most part of material consists of the vertically oriented grain, so we just skip from discussion of this red square. Okay, so because I'm doing all my life simulation, molecular dynamics simulation mostly, so and in this work I perform MD, so I focused here only on MD results, and it of course show basic physical mechanism which we observe. So, however, classical MD cannot apply just from the beginning in simulation because the laser pulse hit first electron subsystem, not ions, and during this non-equilibrium stage where we have a high temperature electron and low temperature ion, electron heating, electron ion energy exchange was simulated by two temperature hydrodynamic codes with a crossing term responding for energy exchange. So this stage lasts several picoseconds, and then we may apply molecular dynamics. So I have to say that in the very thin skin layer, the very high pressure, 1 terapascal electron actually pressure, was formed with a electron temperature about 10 eV. Of course, as I said already, classical MD cannot be directly applied to such warm dense condition. However, because the shock wave propagates faster than the electron heat transport, so we continue our hydrodynamic simulation beyond 300 nanometers from somewhere here in almost more or less cold titanium, where the classical MD definitely is applicable. So you see melting, red indicate liquid state by the atomic order parameter, it's called Q6. So just atomic order parameter which indicate position, which use expansion on spherical function of a local atomic coordinate. So green colors indicate solid phase. Shock wave here, pressure, stress wave propagates, and it looks like a triangle profile, triangle-like profile. It attenuates quickly because release wave here cause expansion of this wave and attenuation as well. And of course, temperature also associated with amplitude of shock wave. Okay, in a little bit more detail about melting. The atomic order parameter illustrate the melting which happens just within shock wave front. This front has a thickness, very thin thickness, about several nanometers. Actually, it's not cannot be distinguished here. So just you see immediately solid melts and some liquid is formed. If we just pick up the temperature of this liquid and pressure, we may compare with the melting line. And we immediately found that material here, liquid state here, is below melting line. So it means it stays in the supercooled metastable state. So this decay of the decrease of the temperature here, the supercooling degree becomes very high, and the crystallization, nucleation of solid phase and crystallization start. Crystallization fronts propagate in backward direction and forward direction, follows the shock front. In the depth about 800, amplitude of shock wave becomes too lower, and the melting, this cold melting, just stops. Okay, it's interesting to plot with profile, triangle-like shockwave profile, spatial profiles, in TP plane, phase plane, in order to demonstrate what the state are formed behind the shock front. Here you see melting line, which separate equilibrium liquid above the line, melting line, and solid state, equilibrium solid state below this one. The dashed line shows the position of shock gugonio, and the shock front located somewhere here. And you see the state here, as I already discussed, in liquid state. However, because they are located in solid, equilibrium solid part of this diagram, so we should conclude that it's indeed metastable liquid. With decrease of pressure and temperature, these metastable liquids start to crystallize in two directions, opposite direction, backward and forward direction. And after about 100 picosecond, all of this liquid becomes solidified. And of course, blue line, blue profile corresponds to the equilibrium solid state on this diagram. I have to say, in addition, that the normal melting on this plot is not shown. I just extrapolate on this right top corner, where the intersection of melting line and shock gugonio indicate position of the onset of the normal melting. So, but we are just mostly concentrated on the cold melting here, and which is why I showed it. Okay, what the main mechanism which results in such unusual cold melting process? We believe, we are sure that enormous shear stress localized within a very thin shockwave front result in instability of the lattice. So the shear stress here and the shock front in our simulation reach about 12 GPa, very huge shear stress. Actually, it exceeds the critical Frankel stress, at which the atomic plane may freely slip on each other in different directions. As a result, the crystal lattice is collapsed, and the supercooled metastable liquid can be formed. The bottom profile indicates that the atomic order parameter just drops significantly on melting front. And then when the crystallization starts again in metastable liquid, it restores to the normal value in the solid phase. So later I will show that, of course, it's not enough to show just configuration, position, or disorder in position to distinguish between amorphization and real melting. And we have to just apply additional analysis of kinetic coefficients like viscosity and self-diffusion in order to prove, in order to confirm that we observe a real melting. Okay, few words about Frankel critical stress, critical shear stress. So it can be reached in uniaxial shock compression of the lattice. Then the shear stress mostly oriented by 45 degree, nearby 45 degree between atomic planes. And this shear stress can be expressed in a simple equation. Sinusoidal equation is, of course, is approximation using shear modulus. So it means it depends mostly on shear modulus. If we assume that the interatomic plane and interparticle, interatomic distance and interplane distance are almost the same, then we have such kind of simple expression. In many metals, such critical shear stress is in the range between 10 and 20 GPa, of course, in undershock compression. So if such condition happens, I mean critical shear stress is reached under shock compression, then what we may say, because there is a family of intersecting slip plane, then free slipping may occur independently in different directions. It means that such a solid under this shear stress cannot resist to the shear. It means it's just liquid. So, but as I said again, we have to confirm it by calculating kinetic coefficients like self-diffusion. So, in order to analyze this mechanism of cold melting, now old paper, almost 10 years old paper, we perform molecular dynamic simulation in moving window and applying of shockwave for aluminum single crystal. So as you see, usually this format, supercooled melt is formed by shock front, and then it recovered to the solid again. So initial state here, just immediately after the shock front, metastable liquid, and they are placed on the liquid branch of gugonium. And then they slowly transform in this aftershock flow to the stable, thermodynamically stable solid state lies on the solid branch of gugonium. So crystallization results in the restoring also atomic order parameter in aftershock flow and the increase of the temperature. It's simply because release of latent heat due to crystallization. So also we observe transformation of radial distribution function and the recovering of long-range order in position of atoms is clearly visible here with the distance on this plane from the shock front. I have to say here an important thing about radial distribution function. Radial distribution function here in melt, in supercooled metastable melt produced by the shock wave is identical to RDF obtained in reference metastable liquid with the same density and temperature. And this reference liquid was obtained not in the shock under shock loading, but by just very fast quenching of the equilibrium, hot equilibrium liquid. And finally, as I promised to show evolution of mean square displacement of atom, and as a derivative, a slope of its self-diffusion coefficient. So you see clearly that at the shock front, the self displacement of atoms sharply increase, and it is associated with a very huge peak of the self-diffusion. Then we have a relatively large slope of liquid, so normal self-diffusion in liquid state, which just the same as in a reference system. And then during crystallization of this metastable liquid, you can see that Mean square displacement go to the plateau almost zero, with almost zero slope. It means the self-diffusion coefficient in solid is near the zero. So finally, I would like to show different regimes of shock wave propagation on the renewed shock eugonio with metastable state. What I add to this diagram, first of all, I add elastic precursor above eugonio elastic limit, and also I put some region, red area, with a formation of supercooled melt. Let's just scan what happened in a solid with increasing of the pressure, or shock pressure. So first of all, just for very, very weak shock wave, we have, it can be only elastic wave, single elastic wave can be observed until the pressure reaches a eugonio elastic limit. When it exceeds, after it exceeds, we have a wave splitting regime. The plastic wave is a slow, this relay line indicates slope of this relay line corresponds to the shock. Plastic shock wave is a slower than elastic precursor, so two waves actually can be observed. And above overdriven state, the plastic branch started where single elastic plastic shock wave can be observed. It's a single but consistent two zone, elastic zone here until intersection of relay line with elastic eugonio, and the plastic wave, plastic zone here. They have a different amplitude but the same velocity, so they propagate as a unique single wave. And above this, in red area, when the stress in the elastic zone, so it means ahead of the plastic deformation zone, exceeds the Frenkel critical stress, the melting, cold melting, begins with red area indicate this regime. So, of course, with a very high, with increasing of pressure, we reach a melting point and normal melting, equilibrium melting, and the liquid branch after this point start. So, in conclusion, I have to say that our experiment demonstrated that two very strong shock wave, melting shock wave, really change microstructure of metal by several micrometers in depth. Newly formed grains are elongated in the length of 100 nanometers and oriented differently in modified subsurface layer. These green points indicate our experimental observation, but our simulation understanding of this process revealed that the shock wave generated in experiment may melt material, even the temperature and melting at shock front is below melting point there at a given time and a given pressure. And as a kind of illustration, I may call the shock front as a meal, because it meals material at atomistic level, and the crystal lattice under such meal becomes unstable because due to very high shear stress localized there. It results in cold mechanical melting, formation of metastable liquid. So ultrafast crystallization after this melting produce a surface layer with a nano-sized grain, which did not exist before. They are oriented specifically perpendicular to the surface, and we believe such surface modification can significantly improve mechanical properties of material. Thank you very much.
Okay. Thank you very much for the interesting talk. So we have some questions. First one.
Not as much a question as a remark. this work has been going on at OIVT for quite some time, and I'm quite glad that it is continuing. Now, if you accidentally run into either Dr. Hrapak or Dr. Filinov, please tell them Peter said hi. Thank you.
Okay, yeah.
Question?
Yeah,
Go ahead.
Peter, yeah, Vorobyov, I remember you, yes.
I have a question, if possible. You presented it's like, the images in the movies which you presented, it was a density field, right? Or a region.
Snapshot, two-dimensional snapshot shows atomic order parameter. Or you mean,
right?
Yeah, with atomic order parameter. It's not density. This parameter is useful to show solid state or distinguish between solid phase and liquid phase, just for illustration.
Is it possible for you also to present like the flow fields?
Yeah, of course, sure. All of this data is available. Just a moment, maybe. In the movie, in the beginning, I already shows pressure profile here. Pressure profile, actually, uniaxial stress, PXX, and the temperature profile. Of course, we have together density, velocity, everything. I mean, all hydrodynamic variables are profiles are available.
And since you mentioned that the shear stress is very important, so this actually looks like more like Richtmeier-Meshkov instability rather than Rayleigh-Taylor, right? In general. Or it's hard to tell.
There is no instability in sense of hydrodynamic, in hydrodynamic sense. There is instability of atomic structure of material due to very high applied shear stress. However, of course, if there is an interface will be on the path of the such shock wave, it may cause a significant change in response of this interface. If such cold melting happened around this interface, it may enhance instability growth rate, and maybe mixing zone will be larger. If there is in comparison with a case where there is no such cold melt.
Thank you so much.
Any other questions? Any other questions from the virtual land? Just unmute your microphone and ask. Sounds like not. I'll just maybe ask one quick question. So the studies you're doing are all in pure samples, I assume? Everything is,
yes.
is purely. What happens if you have impurities, if you have doped metals, and what kind of physical effects might occur?
Oh, there is a lot of additional difficulties appears. Of course, cold melting depends, first of all, on orientation of single crystal. So we perform simulation of 3 main different orientation of our titanium sample. And in all 3 cases, we found 3 different depths where the melting ceases, so stops. So it depends on shear stress, because the shear stress depends on orientation in uniaxial compression. I mean, the depth or melting zone is thickness of melting zone is sensitive for orientation. Not significantly, about plus minus 100 nanometers. In the we have about 800 nanometers here, roughly. Melting depth, but if you have a different direction, then plus minus 50, 100 nanometers depth can be obtained. It is discussed in the paper. So we have initially actually vacation. So, but in order to mimic actually more realistic material. So, the density of vacation was kind of very low, just in normal state. normal condition. So they not at such shear stress they not affect on the melting process and cold melting too. So only important the composition of material, say it's a single crystal or polycrystalline material, and orientation. So polycrystalline material is much difficult to simulate in molecular dynamics because you already see that we did a simulation 1 micrometer length of sample. So it's about 100 million or even 200 millions of atoms was used. So it's difficult to enlarge a sample more to prepare, say, polycrystalline sample. Mm-hmm. So okay. Only we test a different orientation and vacancy concentration.
Mm. Okay, very good. So thanks very much. Let's thank the speaker again.
Okay,
thank you, Vasily.
Yeah, thank you for inviting me for your very good conference site. Thank you very much.
Okay, very good. Okay.